Welcome to our lecture on fundamentals of biomolecules. Today, we are going to explore triacylglycerols. Imagine you have a smartphone and you want it to last for an entire week without charging. You would need a massive, heavy battery pack. In the biological world, living organisms face a very similar problem. They need to store large amounts of energy for times when food is scarce, but they cannot afford to carry around heavy, bulky storage molecules. This is exactly where triacylglycerols come into play. Let us dive in and see how they work. Now that we understand the basic need for energy storage, let us look at what these molecules actually are. Triacylglycerols are the main constituents of body fat in humans and animals, and they are also the oils you find in plants and seeds. Why are they so important? Because they pack a massive amount of energy into a very small, lightweight space. This incredible efficiency is what allows birds to migrate thousands of miles across oceans without eating. And it is what allows bears to hibernate through long, freezing winters without starving. They are truly nature's perfect energy reserve. So, what are these biological battery packs made of? In biochemical terms, a triacylglycerol is a specific type of lipid. It is constructed from just two fundamental building blocks. First, we have a single molecule of glycerol, which acts as the structural backbone. Glycerol is a simple 3-carbon alcohol, meaning it has 3 hydroxyl groups attached to its carbon chain. Second, we have 3 molecules of fatty acids. These fatty acids will attach to the glycerol backbone to form the complete molecule. Understanding these simple components is the first step to understanding how fat stores so much energy. Now that we know the building blocks, how do they actually connect? They join together through a chemical reaction called esterification. During this process, each of the 3 hydroxyl groups on the glycerol backbone reacts with the reactive carboxyl group of a fatty acid. When they connect, they release 3 molecules of water. This creates strong covalent bonds, known as ester linkages. If all 3 fatty acids are identical, we call it a simple triacylglycerol. However, in nature, they are usually mixed, containing 2 or 3 different types of fatty acids attached to the same backbone. This brings us to the mathematical and chemical representation of this process. Here is the chemical equation for the formation of a triacylglycerol. On the left, the term C3H5OH3 represents the glycerol molecule, which acts as the structural backbone. The symbol R represents the long hydrocarbon chain of the fatty acid, and COOH is the reactive carboxyl group. When one glycerol combines with 3 fatty acids, they form the complete triacylglycerol molecule on the right and release 3 molecules of water. If the length of the R chain increases, the melting point and molecular weight of the resulting fat will also increase, turning liquid oils into solid fats. Before we calculate the mass of these molecules, let us understand why their chemical structure makes them so useful. Their primary role is long-term energy storage. Because the carbon atoms in fatty acids are highly reduced, meaning they are bonded mostly to hydrogen rather than oxygen, their oxidation yields more than twice as much energy per gram as carbohydrates or proteins. Furthermore, because they are highly hydrophobic, they repel water and do not carry extra water weight. Beyond energy, they provide vital thermal insulation for animals like whales and act as physical shock absorbers, cushioning delicate internal organs against mechanical damage. Now that we understand the esterification process, let us look at how to calculate the molar mass of the resulting molecule. Because the formation of a triacylglycerol is a condensation reaction, we cannot simply add the masses of the reactants together. For every ester bond formed, one molecule of water is lost. Therefore, the molar mass of the triacylglycerol equals the mass of one glycerol plus the mass of 3 fatty acids minus the mass of 3 water molecules. If we were using a lighter fatty acid, the value of the fatty acid mass would decrease, resulting in a lighter triacylglycerol overall. Let us see this formula in action with a concrete example. We are asked to calculate the molar mass of the simple triacylglycerol, tristerin. We are given the molar mass of stearic acid, which is an 18-carbon saturated fatty acid, as 284.48 grams per mole. Glycerol is 92.09 grams per mole, and water is 18.02 grams per mole. We substitute these known values into our equation. We multiply the mass of stearic acid by 3 because there were 3 fatty acid tails. We also multiply the mass of water by 3 because 3 water molecules are expelled. The final molar mass of tristerin is 891.47 grams per mole. This physically demonstrates how the reaction conserves mass while expelling water. This massive, energy-dense lipid molecule we just calculated leads us to an important question. Just how efficient is it compared to other energy sources? Let us compare fats to carbohydrates. Carbohydrates yield approximately 4 kilocalories per gram of energy, while triacylglycerols yield a massive 9 kilocalories per gram. But the energy density is only half the story. Carbohydrates are stored hydrated, meaning every 1 gram of carbohydrate holds 2 grams of water. Triacylglycerols, on the other hand, are stored completely anhydrous, meaning without water. This fundamental chemical difference has a profound impact on how much weight an organism must carry. To truly understand this efficiency, we need a formula to calculate the mass required to store a specific amount of energy. The raw mass of the lipid needed, ml, is equal to the target energy, E, divided by the energy density of the molecule, dl. The target energy is measured in kilocalories, and the energy density is measured in kilocalories per gram. If the energy density were lower, the required mass would naturally increase. For triacylglycerols, this raw mass will be the final mass, since they do not store water. Let us use this formula to compare fats and carbohydrates directly. Let us apply our formula to a real-world scenario. We need to calculate the total mass required to store 9,000 kilocalories of energy using triacylglycerols. We are given our target energy of 9,000 kilocalories, and we know the energy density of lipids is 9 kilocalories per gram. By dividing the total energy by the energy density, we find that exactly 1,000 grams, or 1 kilogram, of pure fat is required to store this massive amount of energy. Because fat is hydrophobic, no extra water weight is added to this total. It is incredibly compact. Now that we have successfully calculated the mass for lipids, let us prove mathematically why carbohydrates are less efficient for long-term storage. We will perform the same calculation for carbohydrates. Our target energy remains 9,000 kilocalories, but the energy density for carbohydrates is much lower, at only 4 kilocalories per gram. We divide the 9,000 kilocalories by 4. This tells us we need 2,250 grams of raw carbohydrate to hold the exact same amount of energy. Already, the raw mass is more than double that of the lipid. This brings us to the final step of our proof, where we must account for the hidden water weight. Remember, carbohydrates are stored hydrated. Every 1 gram of carbohydrate holds 2 grams of water. Therefore, the total mass equals the raw carbohydrate mass plus twice that amount in water weight. We substitute our raw mass of 2,250 grams into the equation, adding 4,500 grams of water. The total mass required to store the energy as carbohydrates is 6,750 grams. This physically proves why animals evolved to use triacylglycerols. If we stored all our energy as carbohydrates, we would be nearly 7 times heavier and struggle to move efficiently. Let us visually reinforce what we have just learned and proven. Here you are seeing the complete chemical formation of a triacylglycerol. On the left, notice the vertical glycerol molecule with its 3 hydroxyl groups highlighted in red. Approaching it are 3 long fatty acid chains with their reactive carboxyl groups also highlighted. The bold arrow represents the esterification reaction we discussed earlier. On the right, you can see the final, highly dense hydrophobic energy reserve. The fatty acid tails are now securely attached to the backbone via ester bonds, and the 3 water molecules have been expelled. This unique structure is the secret to their incredible storage efficiency. We have covered the full topic of triacylglycerols, so let us review the most important ideas. First, triacylglycerols are the master energy storage molecules of the biological world, acting as lightweight battery packs. Second, they are formed by combining a single glycerol backbone with 3 fatty acid tails through a condensation reaction called esterification. Finally, because they are highly reduced and completely hydrophobic, they provide significantly more energy per gram than carbohydrates without the burden of excess water weight. Understanding these molecules is fundamental to grasping how living things survive, thrive, and manage their metabolic resources. Great job following along.